Welcome to another lecture in our lecture series on design of reinforced concrete structures. Up to our last lecture, we have completed the analysis and design of singly reinforced rectangular beams, and today we will start with doubly reinforced rectangular beams. So singly reinforced rectangular beam is that beam in which the steel tensile reinforcement are only present in the tension zone of the beam. But doubly reinforced rectangular beams entail those beams where the steel reinforcement is present in both the tension zone and also the compression zone of the beam. So doubly reinforced beams have both tension and compression steel reinforcement. Compression steel in addition to increasing the resisting moment. The addition of compression steel in rectangular beams increases the resisting moment of that beam by a very small amount. But the primary thing is that compression steel increases the amount of curvature that a member can take before failure in flexure. And compression steel is also effective in reducing the long-term deflections due to shrinkage and creep. So reinforced concrete beams provided with steel reinforcement in both the tension and compression zones are called doubly reinforced beams. And the compression reinforcement or the steel reinforcement in the compression zone are required in the following situations. We can see three situations listed here. The first is if the architectural requirements restrict the depth of beams such that the beam has to carry moments greater than its limiting capacity. We know that for a given cross section of the beam and for a given material of the concrete, a particular singly reinforced beam has a limiting moment capacity. That means that particular cross section of the beam can resist only up to a certain amount of moment, and we call that MU limiting. Beyond this MU limiting, we cannot increase the amount of tensile steel reinforcement because that will lead to an over-reinforced beam and hence brittle failure in our beams. So, in cases where the depth of our beams are restricted due to various architectural requirements, then in that case, we can use compression reinforcement. Also, compression reinforcement can be used when the bending moment at a section changes sign. For example, if we suppose that this is a continuous beam with some amount of uniformly distributed load, and these arrows represent the reaction forces at the various support points, then if we draw bending moment diagrams of these continuous beams, then we will find that at these support points, negative bending moments arise. So this shaded portion represents the negative bending moment, and at these points, the bending moment changes sign. So at these points or at these places in our beam, we can use compression reinforcement. So this is an example of a continuous beam where we can find that the bending moment changes sign and there is negative bending moment in these areas. Similarly, compression reinforcement are also required to hold the shear stirrups in place and also help to anchor the stirrups. So generally, even in a singly reinforced beams, as we have talked in our previous lectures, there may be some bars at the compression zone also. But that bar will be very minimum and they only perform the function of hanger bars. And these hanger bars are used for the proper anchorage of shear stirrups and to hold the shear stirrups in place. So the more compression reinforcement is there, the more tied up we can make our shear stirrups to these bars here. So among these points, let us say that there are four main uses of compression reinforcement if we summarize these points here. The first is to reduce the sustained load deflections, and that means in reducing the long-term deflections due to shrinkage and creep. Another point is the increasing in ductility of our beams. As we saw in our second point here, compression steel increases the amount of curvature that a member can take before failure. So that is related with the increasing ductility of our beams. The third point is change of mode of failure from compression to tension so that our beam is not over reinforced. And finally, the fourth point is the ease of fabrication. Ease of fabrication not only of the beams but also ease in placement of our shear steelers. So that is about the introduction to doubly reinforced rectangular beams. So for analysis of doubly reinforced rectangular beams, we should know the stress and the strain that is developed in our compression reinforcement. So if you see a diagram here we have assumed that the compression strain in the extreme concrete compression fiber is equal to the maximum usable concrete compressive strain epsilon Cu. So the strain in these concrete fibers at the ultimate stage is the maximum usable compressive strain, and that is taken according to IS code as 0.0035. So this is one of our assumptions in the analysis of doubly reinforced rectangular beams. However, you can see here there are steel reinforcement in the compression zone also, and the area of those compressive steel is represented by ASC. In the analysis of singly reinforced beam, what we assumed that these tensile steel reinforcement in the tension zone reached the yield stress before the crushing of concrete in compression. That is, our steel reinforcement have yielded here. However, it is not reasonable to assume that the strain in the compression reinforcement exceeds the yield strain when analyzing the nominal moment strength of this beam section. So we have to find the level of strain, which is represented as epsilon SC. Epsilon S means the steel and C means the compression. So epsilon SC is the strain of steel in this compression zone, and we have to determine this epsilon SC during the analysis of doubly reinforced rectangular beams. Also, after determining epsilon SC, we can find FSC. FSC is the stress level in this compression steel. So epsilon SC is the strain and FSC is the stress. So how do we determine the strain in our compression reinforcement? We do that by using the concept of strain compatibility. You can see the strain diagram here, and this d dash here represents the distance of the centroid of this compression reinforcement from the extreme compression fiber. So d is our effective depth, which is a distance from extreme compression fiber from the centroid of tensile reinforcement, but d dash represents the distance of centroid of compression reinforcement from the extreme compression fiber. That means this distance here. So using the property of similar triangle here, if we consider one triangle to be this here, and let me draw it with another color, another triangle to be this triangle, then using the property of similar triangles, we can write the equation as 0.0035 over this depth is xu equals to, now the strain at this level of steel reinforcement, we assume that is epsilon SC over, and then this remaining distance will be xu minus d dash. So if you rearrange this equation in terms of epsilon SC, you will get the equation as 0.0035 1 minus d dash over xu. So this is the equation that we use to find the strain in our compression reinforcement, and the same equation is written here. D dash is the distance between the centroid of the compression steel and the extreme compression fiber, as we just discussed. So after determining this epsilon SC, we can find FSC now. So how do we find FSC? The FSC value is given by two different formulas for mild steel and high strength bars or cold deformed bars. For mild steel, it is given as epsilon SC into ES. ES is the modulus of elasticity of steel and epsilon SC is the strain level. So the product of these two terms gives us FSC. And this is the value of FSC for less than or equal to 0.87 Fy. So if you remember our graph for stress to strain graph of mild steel, as we discussed in our previous lecture, we considered a bilinear approximation. So this line represents the level of yield stress of our mild steel, which is Fy, and the line below it is the design curve or design graph, which is represented by 0.87 Fy. So you can say that at this level of 0.87 Fy, then our stress or strain value is constant here. Stress value is constant here, which is 0.87 Fy. But below this point here, that means at a value of stress less than or equal to 0.87 Fy, this curve represents the value of our stress, which is decreasing here. So any point on this line is this value of stress is given as the product of strain epsilon SC into modulus of elasticity ES. So this is the value of stress in our steel for a stress level less than or equal to 0.87 Fy. Similarly, for high strength bars or cold deformed bars, the value of stress is the same again, epsilon into modulus of elasticity, but this is for epsilon SC less than or equal to 0.696 Fy over ES. So how did we get this value here? Another graph, let us see the stress strain graph for high strength bars. So our graph here was approximated as this curve here, and this curve represented our Fy level. And if we draw another curve here, this curve is our design curve, or the curve representing 0.87 Fy stress level. That means Fy over 1.15. However, as we discussed, we know that this stress level or this yield stress value for our SY/ST bars is not definite. So generally, what we take is that at this level, which represents our 0.80 Fy stress level, up to this level, this stress strain diagram can be approximated as a linear curve. So instead of using here 0.87 Fy, we will multiply this thing or this factor by another factor, which is 0.8 over ES. So if you multiply 0.87 into 0.8, you will get this 0.696 Fy by ES. So up to this point, we will consider that this curve is approximately a linear curve. So for a strain value less than or equal to this value here, we will take the value of stress in our compression steel as epsilon SC into ES. So this is about determining the stress and strain in our compression reinforcement before actually analyzing a doubly reinforced rectangular beams. Now, if you remember in our lecture on singly reinforced beam, we determined the depth of our neutral axis by equating the compressive and tensile forces. This compressive force was due to the compressive force of concrete alone, and this tensile force we considered the tensile force due to the steel reinforcement in the tension zone alone, and we ignored the tensile capacity of concrete. But in the case of our doubly reinforced beam, now this compressive force is contributed not only by the concrete in this compression zone, but also by the compression steel reinforcement that we have used here. So now we will divide this C into two things. One is CS, which is the contribution of the compressive force due to the steel reinforcement, that is compression steel reinforcement, plus CC, which is the contribution to the compressive force due to our concrete, equals to T. Now if we do this, let's see here. We have the equation of equilibrium written as CS plus CC equals to T. We know that this CS is given by the formula 0.36 FCK BXU. We have already discussed about the derivation of this part here, and the value of T 0.87 FY/AST. So we will discuss about this 0.87 FY later on. So we have already derived these two parts. Now how do we derive this middle part here? What is FSC, what is FCC, and how do we derive CC equals to FSC minus FCC? So FSC is the stress in compression steel, and FCC, remember, is the stress in concrete, but that should be at the level of centroid of the compression steel. That means at this level. What is the stress in concrete? At this centroid of compression reinforcement level. So FSC is the stress in compression steel, and FCC is the stress in concrete at the level of centroid of compression reinforcement. So actually what we can do is, you can see here there are 3 bars in compression reinforcement and 5 bars in tension reinforcement. So I can represent this single diagram or this single doubly reinforced beam is a summation of a balanced singly reinforced beam. So this doubly reinforced beam, let me write in short form, can be represented as the summation of this balanced singly reinforced beam plus another beam with no concrete assumed here, but only some added steel reinforcement and the compression reinforcement. So let us assume that there is no concrete here, because this concrete we have already assumed in the first part here. If we assume the concrete here also, then it will be double the volume. So we have to ignore the concrete part here. So our doubly reinforced beams, for example, which has here 3 bars in compression reinforcement and 5 bars in tension reinforcement, can be assumed as the summation of a balanced singly reinforced beam with the required amount of reinforcement here, plus another part with some compression reinforcement and some tensile reinforcement, but with no concrete here. So we can just assume it in an equivalent way. Now we know that the compressive force for this singly reinforced section is given by 0.36 FCK/BXU, and the compressive force for the second part is given by the area of the compression reinforcement here. Let us suppose that at ASC into the stress of this compression reinforcement FSC. For now, let us suppose that this FSC is equal to 0.87 FY. So our compression force for the second part will be 0.87 FY ASC. So 0.36 FCK/BXU we have derived this. The stress for our second part, or the compressive force for our second part, will be given by the product of the area of this compression reinforcement and the stress in that compression reinforcement. And if you remember, one thing we have to subtract here. So when we derived our formula for this singly reinforced section, so let us suppose that so if you consider this section here, so here are some steel bars, but now what we have done in this second diagram is that we have removed those steel bars and instead we have used the concrete here. So we have to subtract the amount of concrete, or we have to subtract the compressive forces that is generated due to this amount of concrete, which is equal to in area with this tension steel reinforcement. So if this area is given as ASC here, ASC, and the stress level in this concrete that is present in this same place where the steel reinforcement is present, if the stress level in this concrete is given as FCC, then we have to subtract this portion of our compressive stresses. So you can subtract from either this first value or second value. So you can write here if I use the second value here, minus ASC into FCC. So this ASC we have used because the area of concrete in these three places is equal to, in fact, equal to the area of area of compression reinforcement that we have used, and FCC is the stress level of concrete at these places. So this is the total compressive forces plus 0.36 FCK BXU plus, if you take ASC common, ASC into FSC minus FCC. Now the tensile forces, if we assume the total tensile reinforcement AST1 here and AST2 here, then the tensile forces will be AST1 into FST1 plus AST2 into FST2. If we have assumed that the steels in both these cases have yielded, FST will be 0.87 Fy and AST1 plus AST2 will be total tensile steel reinforcement, which is AST. In this way we get the tensile force. So this is our equation of equilibrium here. If you rearrange this equation, we get the value of neutral axis depth is this formula here. So FSC and FCC we have already discussed, and the value of FCC is given by this formula here now. So now this formula is again derived using the stress strain curve for our concrete, as we discussed when we were discussing the assumptions of limit state method. We discussed the idealized stress strain curve for concrete also. There we assumed that our graph for this stress strain diagram was a parabolic graph up to a strain level of 0.002, and from strain level of 0.002 to our maximum usable strain, which according to our code is 0.0035, it was a straight line. So parabolic and horizontal combination of this was used as the idealized stress strain diagram for concrete. So for the strain in our concrete less than 0.002, this formula can be used to find the value of stress in the concrete at the level of centroid of our compression steel. Whereas if our strain in our concrete is greater than or equal to 0.002 and less than or equal to 0.0035, then we can use the value of FCC, or our stress level in a concrete at this level is 0.447 FCK. So this is our calculation of FCC. Now let us see here. In this formula, we know how to calculate FSC also and FCC also. FSC is given by epsilon SC into ES, as we discussed in our previous slide. FCC is given by this formula here. Now finally, we can calculate the moment of resistance of our beam, and that is calculated by considering the moments of CC and CS about the centroid of the tension steel. The same thing here, force into lever arm. So we have already got the value of CC and CS here from this equation. Now the lever arm for CC. CC means the compressive force due to our concrete. That is already derived in our previous lectures, and that is given by D minus 0.416 XU. And the lever arm for our compression steel is given as D minus D dash. That means if our compression steel is at this level, then the distance of this compression steel centroid from the topmost compression fiber is D dash. Hence our lever arm will be this value here, D minus D dash. So this formula gives us the nominal moment resistance of our doubly reinforced beam. Now let's see here, how do we determine the value of XU here? Although our XU is given by this formula here, how do we determine this XU here? We have already determined FSC and FCC. Now let us determine XU here. So to determine XU, what we will do is, first we will assume the value of XU equal to the limiting value, and that limiting value is given by this formula here. Again, if you don't remember, please revisit our previous lectures on this chapter 3 of our design of reinforced concrete structures. In one of our lectures, we have discussed how to derive this formula for our limiting neutral axis depth. We derived this formula when we were discussing the depth of neutral axis. So first assume that the depth of our neutral axis is equal to the limiting value. Then calculate the strain in our compression steel by using this formula as we discussed before. Because we have assumed the value of XU as XU limiting here, use this value of XU from our step 1 and use the value of D dash from your assumption and calculate epsilon SC. After calculating epsilon SC, you can calculate FSC and FCC. FSC, as we discussed, is given by epsilon SC into ES, and then FCC is given by that big formula as we discussed in our previous slide. And finally, use those values of FSC and FCC in our third step to calculate the value of XU here. Now you have to repeat this process, mainly these steps 2 and 3, until the value of XU that you have assumed at the beginning and the value of XU that you have computed at the last step converges. And finally, after calculating the value of XU, you have to compare that with the value of XU limiting. So in our first step, we have only assumed that XU is equal to XU limiting. But our final answer, XU may either be less than XU limiting, or the value of XU may even come out to be greater than XU limiting. So what happens is XU is less than XU limiting. Then our section is a balanced or an under-reinforced section, and the value of XU that we determine from this procedure is considered to be correct here. And the ultimate moment of resistance in this case is calculated by the same formula that we discussed previously. The same formula here. So this is the case when we get the value of XU to be less than XU limiting. And in that case, we consider that these 3 steps that we followed here to get the value of XU is correct. But if you look at this case 2, when we get the value of XU from these steps that we followed above here to be greater than XU limiting, then ours is an over-reinforced section, and the value of XU is determined by the given procedure is not correct. Now you cannot assume this XU value that you got here to be correct, since this value of XU is determined by considering that our steel has yielded. But when we get our reinforced section to be over-reinforced, our beam to be over-reinforced, then this procedure is not correct. In that case, you can find the value of XU from the equilibrium of internal forces is discussed below. Use the same equation of equilibrium even in second case, that is when XU is greater than XU limiting. But in this case, you cannot assume that the stress in our steel FST is not equal to 0.87 Fy. We have to determine instead the value of FST for our under-reinforced section, our over-reinforced section. So the formula seems to be the same, except that FST is not equal to 0.87 Fy. So how do we determine FST? FST is the stress in tension steel. We know that, corresponding to the strain 0.0035 D minus XU by XU. Again, you can get this from strain compatibility relation by using the property of similar triangles in your strain diagram. FSC and FCC, we know that, and this FSC is corresponding to the epsilon SC 0.0035 XU minus D dash by XU. So how do we determine the value of XU in this case? Do the same thing here. Assume that XU is equal to XU limiting. Use the same formula in the first step. But now determine the value of epsilon ST. Remember, in our previous steps, we did not determine epsilon ST here. We directly determined epsilon SC. But if our beam is found to be under-reinforced, now we have to determine what is the actual strain level in our steel also. So determine epsilon st using this relation here. We know the value of xu from our first step, and corresponding to that epsilon st, find the value of stress in your steel, that is fst, and similarly calculate the value of epsilon sc, that is the strain in your compression steel, and then find the value of fsc and fcc. Now finally compute the value of fu, which is given by the formula here. In this case also you have to repeat these steps until the value of xu converges. So remember, let me just revise from the very beginning. We have to determine the strain level and the stress level in our compression reinforcement. We have discussed the formula here. Since if you remember, or if you just realize what we have done in the analysis of our reinforced beams is that first we have derived a certain strain diagram, and by using that strain diagram we have derived the stress diagram or our stress block here, and from this stress block we calculate the total compressive forces and total tensile forces. Using the equilibrium of that compressive and tensile forces, we determine the value of neutral axis depth, and that neutral axis depth is compared with the limiting value of neutral axis depth to determine the moment capacity of our beams. So we determine the strain and stress level in our compression reinforcement, and then we use that to get the value of the moment resisting capacity or nominal moment capacity of our doubly reinforced beams, and that is given by this formula as we discussed here. And to use this formula we have to determine the depth of our neutral axis xu. First we will determine xu using a certain method here, and we will compare that xu value with the limiting value of xu. If the determined value of neutral axis depth comes out to be less than the limiting value of neutral axis depth, then it will be an under reinforced section, and we use this formula here to calculate the nominal moment capacity. But if the value of xu comes out to be greater than the limiting value, now we have to realize that the procedure that we have used to determine xu is not correct. Instead, we will use a separate equilibrium of internal forces to calculate the value of xu. So this will be our formula here. And again, we have to do some iterative steps to calculate the value of xu until it converges. And then we have to find the moment capacity of our doubly reinforced beams. So this is about the analysis of doubly reinforced rectangular beams. In our next lecture, we will start with the calculation of limiting moment of resistance and compression steel, and then we will look at the design of doubly reinforced beam in our further lectures. So I would like to end today here. We will meet again soon in our next lecture. Till then, stay safe and thank you.